More of section 7. So we left off here. Last thing I had talked about was the relationship between acceleration and angular acceleration, which is a little on the complicated side, actually. As usual, if you have any questions, send them to me. So back in section 1, after having gone through the basic definitions, what does velocity mean, what does acceleration mean, and so on, I said, let's consider a special case. What if the acceleration happens to be constant? There was a list of 5 equations that described uniformly accelerated straight line motion. And we used it to answer questions about, you know, you drop a rock off a bridge, from the time it takes to reach the water, how high up are you, that kind of thing. Sound familiar? Well, we're at the same point now in our discussion of rotation. Having gone through the definitions and related stuff, let's consider a special case. What if the angular acceleration of some rotating object is constant? Well, once again, there is a group of 5 equations. And in fact, if you look at them and think about it, they're the same 5 equations, really. The rotational quantities are defined in the same way as their translational counterparts. If you take the same definitions and manipulate them in the same way, you can end up with the same results. So, for example, this one here looks an awful lot like V final squared equals V initial squared plus 2A delta X, except now we're talking about rotation instead of translational motion. And so it's got a bunch of Greek letters in it instead of the more familiar type. But it's the same idea, just dressed up in a different suit of clothes, okay? And you would approach problems in the same way we did in section 1. I would start out by, before you start just throwing random numbers at random equations, I would start out by making a little list. What are you given? What are you trying to find? That's even more important here than it was in section 1. I mean, back then, you know, A for acceleration was fairly obvious. Now you've got all these cryptic symbols that's like not even our alphabet. And so you need to carefully think as you match up the numbers with the letters and figure out what's being asked for. So as an example of that sort of thing, let's say you're out driving around in the hills south of here, admiring the leaves on a nice October day. And somewhere near the top of a long hill, you get a flat tire. Well, you get out your spare, and then you foolishly, instead of laying it flat on the ground, you lean it against the side of the car instead. And as soon as you turn your back, it begins to roll down the hill. And you turn around 30 seconds later, and your first impulse is to say to yourself, I'll bet that's going about 7 meters per second. Being, of course, an excellent judge of speed. So, based on that information, we're after a couple of things. What is the angular acceleration? And what's the angle it's turned through? Now, if you're a little fuzzy on what letters stand for what, trust your friend, the formula sheet. Angular acceleration, like right there where it says, no, this isn't necessarily the formula you're going to want to use to find alpha. This is just the definition. But as far as matching up this, you know, what symbol are you looking for, and so on, angular acceleration, this is telling you that this symbol goes with this name, and that symbol goes with that name, and so on. So use what you've been provided to get it straight, what the question it tells you and what it's asking. I mean, this one's pretty obvious. R equals 0.35. If you can't figure out that that's telling you R, that's a problem. But this is a little more subtle over here. Meters per second. Remember what I said in the previous recording, a distance unit, anything with a distance unit in it goes with a regular letter, like V. If it was omega, then you'd have an angle unit, okay? So if it's just plain meters, that would be S. Meters per second would be V. Anytime the time unit is squared, that's some kind of an acceleration. Meters per second squared would be regular acceleration A. Radians per second squared would be angular acceleration. So think about all those kinds of things and make yourself a list, kind of like this one. R 0.35 meters. That's the obvious one. Now, it says, well, it doesn't come right out and hit you over the head with it, but it says it starts to roll downhill. So that doesn't say anything about anybody pushing it. It doesn't give you any kind of initial velocity. So apparently it was just at rest and then began to roll away. So V initial equals 0. Also, omega initial equals 0. V, I should probably explain a little bit here. There's the wheel, okay? And as it rolls along, imagine yourself running alongside the wheel. That's a convenient frame of reference to be picturing the wheel from. So you're running down the road. After all, you want your spare tire back. You're running down the road and you're right next to this wheel so that its center is staying even with you. What V means is, seen from that frame of reference, how fast is any point on the edge going around the middle? Now, if the wheel rolls without slipping, that will be the same as, okay, different frame of reference now. You've got somebody who's just standing on the side of the road and they watch your wheel go by. If the wheel rolls without any slippage, that same V will be the speed of the center of the wheel as it goes by that person who's just standing there, okay? If the wheel slips, then they can be two entirely different things. But if it rolls without slippage, V is how fast the center of the wheel moves, and omega is how fast the wheel spins around its center. So they both start out equal to 0. And it tells you the time, 30 seconds. And as I sort of already said, here's the sore spot, okay? Here's where people would get messed up because they would write down omega final equals 7. Don't do that. You'll be sorry. If you aren't sorry on your own, I will see to it that you are sorry. That's sort of part of my job. So what are we supposed to find? It asks for the angular acceleration. That's alpha. And also, how does it phrase it? The angle it has turned through. Well, just like, you know, pretty much, well, it wouldn't be the first day of the course. Back in section 2, I started labeling angles theta, and it's still what's happening now. So, how about this equation? Omega final equals omega initial plus alpha times t. And one more time, because even after one more time, somebody's still going to do this. But do not put the 7 in there for omega initial. My red pen is waiting for you. This is V. V is related to omega by, go over here on the side, V equals R times omega. So if, you know, you're running down the road and the wheel's staying right next to you, if the edge of the wheel is spinning around its center at 7 meters per second, which incidentally is also the speed that you see the road going by from that frame of reference, because the wheel is not slipping across the road. The radius is 0.35 meters. So omega equals 7 meters per second over 0.35 meters. Notice the units have to match. As it happens, the person who wrote the question was being kind in this case. I guess that would be me actually, but if, you know, so they're already both in the same units, but like if one of them was meters and the other was centimeters, you got to match so that they cancel. Meters over meters goes away, leaving you with no real unit in the numerator, which would be radians per second. It is built into this formula that angles are measured in radians. So 20, if a wheel with that radius is going down the road at 7 meters per second, it's spinning at a rate of 20 radians per second. So that, let's see, that was final. So that'll go in there. The initial was 0. Alpha is what I want to know. The time was 30 seconds. So 20 divided by 30. Two-thirds, or as a decimal, 0.667. Radians per second per second. So that's half of what it asks for. We also need theta. Well, there's probably more than one way of doing this, but I went with this one. I know everything in that, so that'll give me the angle in pretty short order. I guess it still shows up over here. Omega initial equals 0. So 0 times the time would still be 0. Alpha, the angular acceleration, that was my other answer, which you can kind of still see the edge of right there. And the time, 30 seconds. About an even 300 radians. Or, if you prefer revolutions, divide by 2 pi. And that'll tell you how many times it went around. Oh, I don't know if it's worth moving the camera and then moving it back again. Let me just read you the next couple of lines on the handout here. It says torque. Torque is to rotation what force is to linear motion. Continuing to parallel what I did earlier in the course. In section 1, I introduced velocity and acceleration and all that terminology that we use in describing motion. And well, see, section 2 was about how to deal with vectors. Section 3 is where I got to Newton's laws, Newton's first 2 laws anyhow. And I said, if you want, I said a force means a push or a pull. And if you want something to accelerate, what you do is you apply a force to it. The bigger the force, the more it accelerates. F equals m times a. Well, if you have something sitting still and you want it to start spinning, instead of making the thing go from here to over there, then what you need to apply to it, like it's a basketball sitting there. If you want it to start spinning, you need to apply a torque, okay? A force means a push or a pull. A torque is when you twist on something. The harder you twist, the bigger the torque. So like it says on the handout, and eventually I'll point it at the thing there, but torque is to rotation what force is to linear motion. Torque is found by multiplying the force by the amount of leverage it has. So as sort of a imprecise definition to get started with, in words, the amount of torque on something is equal to the force times the moment arm. A good example, let's say, well, I was just talking about having a flat tire. So let's say you get your spare tire back, and now you need to take the wheel off so that you can remove the flat and put on the spare. Well, there's those lug nuts you have to take off. Now, if you've got some little short wrench like that, you're going to have quite a hard time getting those off, because on a good day, when things aren't all rusted up, it takes maybe around 100 foot-pounds, give or take, to minimum. Like I said, if they're all rusted up, it'll be more to get those loose. So if you've got some little toy wrench about that long, you're not going to be able to do it. But you get the nice long wrench, and you don't get any stronger. But now, if let's say if you lean right back and get a good grip, maybe you can exert a force of 100 pounds on that wrench. No, let's make you a little weaker. Let's say you can pull with 80 pounds, okay? It's going to take 100 foot-pounds to loosen up that nut. You can pull with a force of 80 pounds. If that wrench is 1 foot long, 80 pounds times 1 foot, you're making 80 foot-pounds of torque. And if it takes 100 to break the thing loose, it's not going anywhere. If you get a wrench that's 2 feet long, you didn't get any stronger. You haven't been taking vitamins or something like that. You're still pulling on it with a force of 80 pounds. But you multiply that by a wrench that's 2 feet long. Now you're producing 160 foot-pounds of torque. Well, that's way more. I mean, you aren't going to have to pull with 80 pounds this time, because all you need is 100. And so, 160 is kind of overkill. So that's the idea. How hard do you pull times how much leverage do you give it? This is why, laying around in my stuff, I have an old piece of steel drain pipe about that long, because when the breaker bar alone isn't turning it, rather than, there have been times I've stood on wrenches, and that usually does it too. But if you take that piece of drain pipe, slide it over the handle of the wrench so that you now have a lever about this long, one of two things is going to happen. You're either going to one of three things. You're going to loosen up the nut, which would be the good outcome, or you're going to break the bolt, or you're going to break the wrench. There is no fourth possibility. You're going to get what you want, or you're going to break something when you've got a lever that long. So helps if you spray a little bit of that penetrating oil on there too. But anyway, moment arm is kind of a fancy way of saying the amount of leverage that the force gets. That's the amount of leverage. And the tricky thing that catches people sometimes, the leverage has to be measured along a perpendicular. I didn't feel like writing out the word perpendicular. I just used the little mathematical symbol. So what do I mean by that? Well, come over here and I will show you. So here we have some kind of lever-like thing which is pivoted at one end. That could be a wrench trying to turn a nut or a bolt, or it could be that door over there looking down at it from above. Somebody sawed a hole in the ceiling and they're looking down at the door from above. So that could be, or it could be a trap door in a floor, and then you don't have to saw a hole in the ceiling. Whatever it is, there's a hinge on one end, some point that it can rotate about like that. And there's a force acting on this. Now, if the person exerting the force has any sense at all, they'll be creating the force perpendicular to the wrench, because that's the most effective way of doing it. But yeah, as the expression goes, common sense is surprisingly uncommon. You don't have to have the force perpendicular to the wrench. Hypothetically, it could be at any angle. So let's just draw it at some random angle, the angle between the force and the wrench or door or whatever that is is theta. If you take the arrow that represents the force and extend it in both directions, in principle, extend it to infinity. In practice, you don't have to draw it quite that far, but that is called the force's line of action. As with a lot of things, its name basically tells you what it is. It's the line along which the force acts, hence the name. So take the arrow for the force, extend it in both directions. The moment arm, or some books call it the lever arm, means how far is this pivot point from that line. Now, the distance from a point to a line is measured along a perpendicular, okay? If somebody asks me how far am I standing from that wall, I don't know if you can see in the camera how far I'm standing from the wall, but you would expect me to measure that distance right over along a perpendicular to the wall like this and say that I'm about 2 feet from the wall. The way you don't do it is, imagine I've got a tape measure and I've laid it across the floor at a really shallow angle to the wall so that the end of the tape measure, 0 feet, is right up against the wall over there someplace. And that tape measure comes along and makes like about a 10 or 12 degree angle with the wall. And right here between my feet, it says 15 feet on the tape measure. And I stand here and I try and tell you, I'm 15 feet from the wall. See, one end of the tape measure's on the wall, and the other end right here where I am, it says 15 feet. I'm 15 feet from the wall. No, I'm not. I'm 2 feet from the wall. You're supposed to measure it along a perpendicular. That's me. That's the wall. The right way to measure the distance from here to there, like that. So that, I'll label it with the letter L. L for lever arm. That is F's moment arm, or fairly often it's called the lever arm. Pick your favorite terminology. But the point is, if you want to determine how much torque that force produces, it's the force times the moment arm, okay? How hard are you pulling times how much leverage do you give it? You get the maximum torque from a given amount of force. As I said earlier, if theta is 90 degrees, if you're pulling like that, you get no torque at all if theta is 0 degrees. Here, if I can aim this at the door, I will demonstrate. So there's the door to the lab, and if I exert, does that show up? Yeah, that'll be in the picture. Notice, no matter how hard I pull on this door, if I'm pulling it this way, it didn't make the door turn, okay? No matter how big the force, if the force acts in this direction, you see if that's the force, its line of action goes right through the pivot point. And so, even if I was pulling with 100 pounds, 100 pounds times nothing, nothing being the distance from that point to this line, 100 pounds times nothing is nothing. It produced no torque. And so you get a minimum of torque if theta is 0, and you get a maximum if theta is 90 degrees. Now, let's see. Taking, I can squeeze this in on the bottom. Taking what I had in words over here and writing it in symbols instead. The symbol we're going to use for torque is a Greek letter tau. It's a Greek T, okay? T for torque. The textbook, I think, actually uses the letter D rather than L for the lever arm, but I don't like that. That looks too much like a differential for my taste. So this is not the only place where I'm going to do things a little bit differently than the textbook. Like any of you read the textbook anyhow. Well, probably a few of you do. And if you do, you'll see there's a little difference in notation here. Now, notice, well, first of all, I'm going to call the distance from there to there call it R for radius, because as this thing rotates, the end of the wrench moves along a circular path of radius R. So R is the radius out to the point where the force acts. It is often convenient to have an expression for the torque in terms of R instead of L, because L is this thing that's measured through empty space to this imaginary line that you can't even see. And wouldn't it be nice instead to have something that involves a distance where you can actually hold a ruler right next to the wrench and measure how long it is? So if this is theta over here, that would also be theta over there. They're vertical angles. So we've got this nice little right triangle. I'll make it again in miniature down here just to be sure, draw it without all the clutter around it. And on the hypotenuse, we've got R. Over here, we've got theta. It's kind of small, but yeah, that shows up all right on the screen. It's not like anybody's watching me from the back row today. Over here on the opposite side, that was the moment arm, L. Well, as I've probably mentioned once or twice before, if you've got a right triangle, the opposite side equals the hypotenuse times the sine of the angle. So L equals R sine theta. And so if you take R sine theta and stick it where the L used to be, torque equals force times R sine of theta So torque, units. Newtons times meters, okay? Force times moment arm. The force is newtons, the moment arm is meters. Incidentally, just a little footnote here. A couple of weeks ago, we did work and energy. Work was force times distance. That was also newtons times meters. And I said a newton meter is equivalent to a joule. A joule is meant to be a unit of work. In the context of torque, you would not call this a joule. Torque and work are two entirely different things, okay? If I've got a door pivoted over there, P for pivot, and I push on the end of it until the door is over here instead, okay? Before and after, somehow the door got a little bit longer. Maybe I should fix that. If you want to calculate how much work this force did, it would be the force times this distance, the force times the distance which that force acts through. If you want to calculate the torque created by that, it would be the force times this distance, the amount of leverage it has. So even though they happen to be dimensionally equivalent, torque and work are two entirely different things, to the point where work is a scalar and torque is a vector. So anyhow, the Newton meter is called a joule if you're using it as a unit of work or energy. The torque, you usually just call it Newton meters to make it sound a little different, because torque is something different. So it's the newtons times how many meters of leverage, assuming that the meters are measured perpendicular to the newtons. If the meters are not measured perpendicular to the newtons, you have to compensate by slipping in a factor of sine theta. If they are measured perpendicular to each other, well, the sine of 90 degrees is 1, and you've just got force times the radius that way. Okay, so that's what torque is. Let's point you back at the script here for a moment. Let's see where we are. Where we are is we're completely out of focus again. I don't know why you think that's the way you should be focused. Sometimes this makes it focus. Sometimes it doesn't. Try this. Come on. Focus on the piece of paper. Ah, got it. And there it is. Okay. So I kind of said this like 10 minutes ago. Torque is to rotation, what force is to linear motion. Torque is found by multiplying the torque by the moment. Oh yeah, plus and minus signs. As I said, torque is a vector, but if you restrict yourself to problems in a plane, which is for the most part what I'm going to do, then there's only two possible ways you can make something rotate. You can either twist something to try and make it turn counterclockwise, or you can twist on it to try and make it turn clockwise. The usual convention is to say counterclockwise is positive and clockwise is negative. well, you know, like saying up is positive and down is negative, that's kind of an arbitrary convention. You could get things to work the other way, but well, it might not be the best possible idea for reasons that I'll get to soon. But that's, well, like in this next example, you've got 3 books sitting on a seesaw. Hard to find a playground that has a seesaw anymore. There were pretty much standard seesaws and swings, pretty much standard equipment when I was a kid, but I think somebody fell off and broke their arm or something. Don't see them too often anymore. Anyhow, you've got a board pivoted right at its center, and so you know it can rotate like that. And we want to find the total torque due to these several different forces that are present. And what you have to do is calculate each torque from the definition that I just talked about. And then you have to add them up to get the total, keeping in mind that torques in opposite directions should get opposite signs when you add them together, okay? This is trying to turn the seesaw in one direction, and the other two are trying to turn the seesaw in the other direction. And the usual convention is to say that, you know, counterclockwise is positive. So that's what's going on there. Details will be over here. Summation of the torques on that seesaw. Maybe it'd be good if I had a little sketch of a seesaw that was in the picture at the same time. So we had let's see, 4, 2, and 4. This one was 40 newtons, 4 meters away. Here we had 30 newtons, 2 meters. Four meters and 15. Okay, so I'll just start here and work my way along. 40 newtons times 4 meters, force times moment arm. If that was the only force acting, it would make the seesaw rotate this way. Counterclockwise is positive, so that term gets a plus sign. 4 meters, 40 newtons. Both of the others, if either one of these were the only forces present, they would make the seesaw turn the other way. That's clockwise. So both of these get minus signs, okay? Notice that plus and minus is no longer a matter of up versus down. All 3 of them point down, okay? Rather, plus and minus is now clockwise versus counterclockwise. So minus 2 meters times 30 newtons, and also minus 4 meters times 15 newtons, 160 minus 60 minus 60. I suppose it's not really necessary to write the plus sign. I just wanted a little extra emphasis. The fact that it comes out positive means that the overall total effect is counterclockwise. So even though there's more weight on the other end of the seesaw, you've got a total of 45 newtons over here and only 40 on that side. Because of the differences in leverage, this one wins. And if you let go of this, this end will go down and this end will go up. The net torque is counterclockwise. Now, there are a couple of other forces that I didn't bother to, this was not a complete diagram of all the forces acting on this. I only drew in the ones that produce any torque, but a complete diagram would have showed a couple more forces. First of all, there's the supporting force from the pivot here. Okay, all of these pull down, but the whole seesaw doesn't collapse downward. There's an upward force to counterbalance them, and that comes from the support here. So there's an upward force, but it produces no torque because it acts right at the pivot point. It would be like if I went over there and started to where the door is, and I started shoving on the hinges. No matter how hard I push on the hinges, I can't close the door that way because, you know, force times moment arm, the moment arm is zero. My force is passing right through the pivot point, and so it gets 0 meters of leverage, okay? So because this is acting right at the pivot, that supporting force produces no torque. Then there's a matter of the weight of the seesaw itself. You've got a wooden board here and it weighs something. I didn't put its weight in there. Now, here's what's really happening, okay? The weight of an object is actually a distributed force. So if you've got a board like that, pivoted here in the middle, doesn't matter where it's pivoted, the story is the same. That little piece of it weighs something, the next little piece of it weighs something, the next little piece of it weighs something. That board is basically a bunch of pieces of sawdust that haven't been separated from each other. Each one of those little parts of it creates a small force. They're all at different distances from the pivot point. What you have to do is add up the torque produced by each little part from going from one end to the other. In other words, you have to integrate, and half of you don't even know what that means. And besides, even if you did know what that means, that's a kind of a lengthy, cumbersome process compared to playing a little game of let's pretend, okay? Let's play some little tinkly music and go off to the neighborhood of make-believe. Instead of having this whole forest of little tiny arrows that goes from one end of the board to the other, let's instead pretend there is just one big arrow. And the point where we put that arrow is called the object's center of gravity. Now, like I said, what it really is it's a distributed force, and for certain types of problems, you have to look at it that way. For example, if you want to figure out how much the board sags under its own weight. But for any problem that we'll encounter in this course, anyhow, you can get away with this simplification. The weight of the thing acts at a single point called the center of gravity. And if it's a uniform object, if one end isn't thicker than the other, or one end isn't denser than the other, or something like that, the center of gravity is just right in the middle of it. Now, if it's not a uniform object, like this pencil, it's a very interesting pencil. Somebody left it here. It's not actually, well, it's my pencil now, but some student left it here at some point. See, if you support something at its center of gravity, the weight produces no torque, and it doesn't have any tendency to rotate off of my finger and fall. And you can see the center of gravity is not in the middle because, well, there's metal down here, and that aluminum is probably 5 or 6 times denser than the wood that the rest of the pencil's made out of. Over here on the other end, it kind of tapers down and gets skinny, and so the center of gravity is closer to the heavier end. So, non-uniform object, it's not in the middle, but for any uniform object, the center of gravity is just right in the middle of the thing. So, to summarize some of what I just said, that's supposed to be an H. The beam's weight guess would help if I moved the camera over, wouldn't it? The beam's weight and upward force at pivot produce no torque because R equals 0. And the formula back over here, R is the distance from where the force acts to the axis of rotation. Well, the supporting force and the weight both act right here at the axis of rotation. So R equals 0. And so the force times 0 gives you no torque. So I guess it's time for me to move the page up a little higher. That's what it's time for. I already said all of that. The torque from an object's weight is the same as if the weight was concentrated at a point called its center of gravity. For a uniform object, it's just in the middle of it, the geometric center. Okay, so now we come down to where it says the rotational counterpart of Newton's second law. Back in the earlier part of the course, I said a force means a push or a pull, and that if you push or pull on something, it makes it accelerate. Forces cause acceleration, which led to the question, how much acceleration do you get from a certain amount of force? And the answer to that was Newton's second law, F equals ma. If you know how much force is being applied and you know the body's mass, you can get the acceleration from that. So the question right now is, I've said torque causes angular acceleration. Something is at rest and you apply a net torque to it, it'll begin to spin faster and faster as that torque twists on it. How much angular acceleration do you get from a given amount of torque? We need some equation that'll do for rotation what F equals ma did for translational motion. Well, let me explain that to you. That'll probably take 10 or 15 minutes. I might very well end the recording at that point, but we'll see how fast it goes. I think I already did this once before. I said, let's at least start out with the simplest case, which is some small point-like particle, and then I'll generalize from there. But let's see, the center is probably around there, give or take. And we've got some mass m, which is following this circular path. I think, was it the previous recording, the earlier part of section 7? I don't remember, but I said something about, imagine you're on a frozen pond and you've got like a hockey puck and a little bit of duct tape and some string, and you tape one end of the string to the hockey puck, and the other end of the string, there's like a cattail or some sort of plant sticking out of the ice over here. And you make a little loop in the string and put that around the plant. So there's where the plant sticks out of the ice, a little tree or something like that. And there's the piece of string. There's the hockey puck. And you're pushing on that with your finger so that as time passes, it goes faster and faster and faster and faster, okay? You are creating a tangential force, Ft, with your finger, while the string creates a force toward the center, a centripetal force, or a radial force, if you'd rather. Maybe R is the radius of the circle. I did not get that center at the center, did I? From there to there is definitely more than from there to there. Well, what are we going to do? Going to assume that this mass is located at a single geometric point. In other words, that from one side of it to the other is a distance of exactly 0. This, of course, is silly. It's another one of those approximations that I talked about a while ago that introductory courses are just full of, like frictionless surfaces and things like that. But it's often a useful simplification. Well, for example, if you want to talk about the Earth orbiting around the sun, saying that the Earth is located, the mass of the Earth is located at a single point is actually a very, very good approximation, because the diameter of the Earth is only 8,000 miles. Maybe the thing to do is compare radius to radius. The radius of the Earth is 4,000 miles. The radius of the Earth's orbit is almost 100 million miles. That's like 4.5 orders of magnitude different, if I did that correctly in my head, unless it's 5.5. So for a problem like that, you can, to an excellent degree of accuracy, say all that mass is located at a single point. On the other hand, if you decide to walk from here to Argentina, the Earth is definitely not a point particle. But as long as this is very small compared to that, it's a very good approximation, and that's what we're going to assume here. So each of these forces has its own distinct effect on that particle. more space over here. Tangential force makes it go faster and faster. In other words, the tangential force causes tangential acceleration. Tangential acceleration is caused by the change in speed. I talked about that in the previous recording. The centripetal force makes it follow a circle. So this force changes the magnitude of the velocity. This force changes the direction of the velocity. One causes the tangential acceleration, the other causes the centripetal acceleration. And actually, I'm being completely general here. This doesn't necessarily have to be a hockey puck tied to a cattail. This could be anything that's moving along a circular path. There might be 41 different forces acting on it, and you resolve them all into components along and across the direction of motion. And this would be the summation of the forces in a tangential direction, and this would be the summation of the radial components, okay? So I'm interested in a relationship between torque and angular acceleration. Maybe the way to go looking for that is to start out by calculating the torque on this thing. So summation of the torques about point C. And when people put a subscript on that, they're labeling where the pivot point is. So summation of the torques about point C. Well, that would be the torque due to the one force plus the torque due to the other force, each of which is given by the expression that you can't see me pointing at, but remember this back over here? R times F times the sine of the angle in between is the torque due to a force. So applying that to the tangential force, R times F times, well, the angle between the radius and the tangential force is 90 degrees. Sine of 90 degrees, 1. And then there's the centripetal force. If you think of a radius vector, it points from the origin to the particle. So the R vector points outward like that. The force vector points right along it the other way. If you stick the two of them together, they'd make a 180-degree angle. Well, without getting quite so mathy about it, just look at the picture. The force passes right through the center of rotation. That's like me going over to the door and shoving on the hinges. That's not going to produce any torque. A force that passes, or when I turned the camera and pulled on it, right straight out. So my line of action passed right through the hinges. no torque. So, kind of used up some of my space over here, but the summation of the torques is equal to R times the tangential force. The centripetal component is 0. It produces no torque. The tangential force would equal the mass times the tangential acceleration, Newton's second law. In the other term, the centripetal force would equal the mass times the centripetal acceleration, but I'm not going to write that down because it just gets multiplied by 0 anyway. From what I said earlier in section 7, tangential acceleration is equal to R times alpha. This substitution requires the use of radians. So, whatever I come up with at the end of this will require the use of radians. If I try and measure in some other unit, it will invalidate this step in the derivation and make the formula I'm coming up with untrue. So we've got two different R's. Let's combine them. The quantity in parentheses, mr squared. I feel like giving that a name. Bill or George doesn't seem appropriate. How about calling it the particle's moment of inertia? Going to represent it by the letter I. I'm not going to put a box around that part yet because I'm going to generalize this before we're done. But the summation of the torques on a point-like particle is all I've talked about so far. But there is your rotational counterpart for Newton's second law. For translational motion, summation of the forces is equal to m times a. For rotational motion, summation of the torques equals I times alpha. Remember, as I pointed out when I used this back here, it only works if you measure in radians per second per second. What I always say is, when in doubt, convert to radians. It's not always necessary, but it's never wrong, okay? There are some equations, like the ones I used when that tire was rolling down the hill in that problem, like omega final squared equals omega initial squared plus 2 alpha theta. Yeah, that one's a very easygoing equation. It doesn't care. You can use revolutions, you can use degrees if you want to. As long as it's the same unit all the way across the equation, you're good. But then there are others, like this one, that are more particular. And if you don't use radians, it's wrong. So not always necessary, but when in doubt, convert to radians. The worst that can happen is you make the solution longer than it needed to be.